have to log in. So good evening, everyone, and welcome to CAWASA webinar 2021 series number 11. And the topic today is how to find a needle in a haystack, the case for district metered areas and its importance in non-revenue water. This afternoon, our webinar is being presented, complements Operators Without Borders. And I'm going to invite Ms. Valerie Jenkinson, the chair of the Operators Without Borders, to give us an overview of the seminar, of the webinar, and then to introduce our guest presenter, who is no stranger to us. He has presented to us previously. So I'd like to welcome our guest presenter, Mr. Carl Yates. Over to you, Valerie.
Thanks, Ignatius, and hi again, everybody. It's lovely to be with you again. So Carl, as I have mentioned to those of you who were on one of his webinars before, is one of our most senior utility managers in Canada. He has extensive experience in the water utility profession, and most recently was the general manager of Halifax Water from 1994 to 2019. When he retired, but he failed retirement, and he was quickly snapped up to run a wonderful pilot project in Canada, the very first ever, and he is the Chief Executive Officer now of the new First Nations Indigenous water utility, which is all the maritime provinces. And so this is a tremendous honor for Carl, and probably a lot of hard work, and he's hard at it, but we couldn't let him retire and lose his experience. But when it comes to water leakage, he is one of the champions in Canada. And we talked about before when he was working with you that his water leakage is down to 1.5% in Halifax Water when he left, which is absolutely outstanding. It's one of the things that we can only dream of in the Caribbean. So he is now running this, but he's going to share his expertise with us today. He is an engineer, has a Bachelor of Engineering from Memorial University of Newfoundland. So if you think he talks a little different than a lot of Canadians, you're right. He's what we call a newfie. And then he has a Master of Applied Science for the Technical University of Nova Scotia, which is now Dalhousie University. Some of you may have even been to Dalhousie yourselves, because we do train a lot of Caribbean engineers. He previously served as the director of the Water Research Foundation, with roles as chair of the Research Advisory Council and Focus Area Council. And he's the chair of Canada's Natural Research Research Advisory Council, and has a whole slew of things. It would take almost as much time as this whole webinar to go through all the things that Carl has done. So I'm going to hand you over to him and let him take this away and give you his expertise on water metered areas. Thank you, Carl.
All right, thanks, Valerie. And I actually thought it was you who had the interesting dialect. So there you go. I guess that depends on where you sit, how you view that. With that, I guess I'll try to share my screen and pop up the presentation. All right. Well, I'm going to hopefully give you some of my my views from the work that I did with Halifax Water. This is where a lot of this stems from. We've been involved at Halifax Water formally in water loss control since the 90s. So I'll take you through that journey, and hopefully you'll get a sense of why I call finding a leak like finding a needle in the haystack. And often the best way we can find that needle, I like to say, is to break up the haystacks into several haystacks, which is what DMAs are all about. So with that, we'll as they say, provide a word from our sponsor. I'm here on behalf of Operators Without Borders. I'm actually a director of the board, and I'm very pleased to continue to support sustainable water management, which obviously includes being good stewards of water resources. So our objective, of course, at the Operators Without Borders is to assist water and wastewater utilities in developing countries recover from disaster situations and build capacity through training and mentoring of water and wastewater operators. And as you can appreciate, last year was challenging times, so not a lot of assistance was done on the ground, but we certainly pivoted last year, like many organizations, and did a lot of our training and our support by online and virtual means. So pleased to continue that perhaps for the next few months, and maybe we get fortunate by the fall, they may let us travel safely again. So in terms of where the context for water loss control is coming from, I'd like to point to some new things that happened actually back in the 90s when at Halifax Water, we were certainly trying to get a handle on our leakage. We had serious leakage problems at that time. We just came through a merger and we actually took over a greater responsibility in the Halifax area. And we had some very pressing needs to actually stem leakage because we're building a brand new treatment plant. So we actually had an absolute reason to be very careful about wasting the water that we were about to produce through a brand new treatment plant. So we were looking initially in North America, and I can tell you that we did not like what we saw going on in North America at the time. So we did actually look to Europe at the time and discovered that the International Water Association had put together a task force to look at this very issue, to kind of look at a better way of controlling water losses. And they had a lot of experts in the field on a task force to try to develop it. The good news is, however, there was a representation there from the American Water Association as well. So they were also engaged to try to find this new way of dealing with water loss. As I mentioned, what we saw in North America was not best practice. There was a lot of discussion around the so-called reduction of unaccounted for water. So as soon as you hear that term, I always say it's got some negative connotations just by the name itself. But we weren't really seeing any advancements. It was really old and stale, and not much progress had been done for really, I'd say 40, 50 years. There was no real difference in behaviors or outcomes. So the big thing we saw, of course, is absolutely no consistent approach in North America. It was just a helter-skelter, no standard terms, no defined methodologies, just people doing a bunch of different things, but not doing it well. So that's the context. So the thing about the IWA methodology, which came to be really at the turn of the century when they put this methodology out for the world to see, is we like to say it has a place for everything and everything in its place. So the key thing about this methodology, you actually start with a water audit. So basically you look at your system and you determine where is the water going, how is it being used, and you document it to the best of your ability. And what you're really doing here, of course, and this is good engineering practice, and I apologize for my Jack Russell just barking in the background. What you're doing with this audit is you are defining the problem. And of course, those of you that have an engineering background understand how important that is. There's no point in looking for solutions until you define the problem. So here you see the standard water balance that's portrayed by the IWA methodology. On the left, you start with your system input. So hopefully you know what's coming from the treatment plant. You have it broken down into authorized consumption. That's hopefully what you get revenue from for the most part. And also, of course, water losses. So to speak to the water losses here on the chart, that is also broken down into two categories: apparent losses and real losses. And of course, today we're going to spend a lot of time on real losses, but certainly is worthwhile to note what apparent losses are as well. And they would be broken down into things like unauthorized consumption and customer meter inaccuracies. So to name it, unauthorized consumption is simply theft. And that happens in all utilities, even including at Halifax Water. So we have indeed curtailed some of that as a result of the work promoted by the IWA methodologies. But also customer meter inaccuracies is also something that comes to bear. Sometimes if you're taking manual readings, if you're inputting from one system to another, you can make errors during that transition, or sometimes your meters are just plain old and worn out and are just no longer accurate. So those are what we'd call apparent losses. So once those are fixed, then those losses obviously are immediately curtailed. And these are often of higher value because often that is your retail value. And that is obviously the highest cost that you can recover. So in terms of real losses, that's kind of more of that one that takes perhaps a back seat, but shouldn't, because it represents huge economic losses for utilities. So what we're speaking about, of course, is things like leakage on transmission mains and distribution mains, sometimes leakage through reservoirs or even overflows at reservoirs, and of course leakage on the service connection points up to the metering within each premise. So all those services that come off the distribution mains indeed contribute to leakage. So in addition, we talk about on-billed authorized consumption. You can see that category there, and that's broken down into on-billed metered consumption and on-billed unmetered consumption. And I give you an example of both of those from a practical sense. An example for on-billed meter consumption, and this is something that could happen in any utility. During construction, you might provide water to a contractor to do the work that they had to do, and you might put a meter on a hydrant, and because they're doing the work for you, you just say that's part of the relationship with your contractor. You don't actually send that contractor the bill, but yet it's metered. You actually do know what's being consumed. And that's a good thing, because now you can account for it and put it in the spreadsheet to say, okay, I know where that water is going, and that's okay. And unbilled, unmetered consumption is a very obvious one in most municipalities, certainly in North America. And that would be water used for fire protection. It's actually not metered. The fire department hooks on to fire hydrants. There's no real meter on that hydrant per se. You can still detect how much is being used through other means, through the SCADA system that a utility might have, but nonetheless, you're actually not going to bill the fire department for that usage. So it's on-billed, it's on-metered, but it's absolutely authorized consumption. But all told, all those three categories, of course, make up non-revenue water. And that is really what we're after. We're trying to minimize our non-revenue water so we can have a sustainable utility that stand on its own 2 feet in terms of finance. So there's 4 strategies that are promoted by the methodology, and we're going to speak to at least 3 of these today. We're not going to spend much time actually on the one on the bottom. This is about asset management, and that's a whole presentation for another day, but certainly you all understand how important it is to keep your assets in a state of good repair and look long-term when you're looking at your replacement schedules. But today I'm going to focus mainly on the 2 side arrows, I'll call it, because those are the ones that affect leak runtime. And we're going to spend a lot of time talking about reducing leakage runtime. Up above, also want to point out, however, the methodology called pressure management, and I'm sure many of you are using this today, which also will provide better service to your customers, but certainly minimize your losses. And it's the only one that shows that things can go 2 ways with pressure management. You can have more leakage if you've got more pressure, or you can have less leakage if you have lower pressure. And that's what that double arrow is meant to reflect. And in the box in the middle, that is really what the outcome we're looking for. We're trying to minimize our real losses, and that is something we calculate with that audit I just showed you. We actually know what that is based on that audit that we partake. And then what we're trying to do is get as close to the unavoidable annual real losses as we can. So that's that light blue box you see right in the center of your screen. In some cases, we can get this dark blue box very close to the unavoidable annual real losses. But sometimes it actually may not be worth our while to absolutely close that entirely, to have, shall we say, perfection within our system. And sometimes I say that because it's not economical all the time to chase all your losses. However, the majority of your leakage is very economical to curtail, and that we'll talk about today. So that box ratio you see there, the calculated annual real losses, Carl, divided by the unavoidable annual real losses, is a metric that's used all across the world. And it is the most famous metric promoted by the International Water Association. And it has a name, and it is called the Infrastructure Leakage Index, ILI. And it is definitely one of the best benchmarks I've ever seen for any outcome for a water utility. And I can make the broad statement to say that if you do water loss control well, you will do all other things well. Because in order to do water loss control well, you need to really understand your system and be intimate and have great knowledge about your system. For those of you who like to read manuals, this is a lovely manual where you can learn all about this new methodology. This is called the M36 manual. It's publicized now by the American Water Works Association, and it contains that methodology that was developed back in the late 90s. I mentioned, of course, that there was a representative from the American Water Works Association on that task force. And as a result, that best practice got, should we say, brought to America and now is embedded in this manual. So for those of you on the call, hopefully some of you have already been delving into that manual, but if not, it could become a best, seller for you because it'll actually make you a better manager if you adopt the methodologies in it. So to talk a little bit about leakage, because it's important to understand the different types of leakage. If we're going to try to control it and reduce runtime, we need to understand what it is we're looking for. And there's three types of leakage that utilities have to deal with. And starting on the far left, we'll talk about background leakage. That's the leakage that you'll see at every joint pretty much in your system. It's a little bit of weep here and there. It's not anything you're ever going to find by any of the usual methods of acoustic leak detection. You might discover it when you dig in the street. You might get down close to the main. You might see a little bit of dampness around a joint. That is not necessarily going to give us a lot of concern. So that's not actually what we're after. So we can set that aside. We know it's there, and there are ways we can still control it by pressure management in particular, and I'll explain that later. But certainly, we're not going to be trying to put out leak detection teams to find that background leakage. And if you go to the far right, you'll see the term reported leakage. And this is the one, of course, is easiest to find because this is the one that surfaces. You see this running down your street. Sometimes even the customers will call it into your call center and say, look, there's a problem here in the street. You better come out before this whole thing gets out of control. And sure enough, you will get out there quickly and shut that main down because this is the leak, of course, that can blow up the street. It can cause a lot of damage, cause a lot of liability for the utility, and certainly one to be avoided as much as you possibly can. There are obviously tools to deal with these types of things. If you have a lot of additional leakage and a lot of breakage in one street, of course, the obvious technique is let's replace this main, no question. And I'm sure many of you have done that. But in terms of reaction, you better get out in a hurry and fix that. So being able to mobilize a crew at a very short notice is very important to deal with that type of leakage. The leakage we're going to spend most of our time today talking about, however, is the one in the middle, and that is the one called unreported leakage. This is the leak that often does not come to the surface. It stays down, it leaks through the gravel within the pipe bedding, or sometimes it even finds its way into a storm sewer or a sanitary sewer, and then you end up treating it and pumping it downstream again, which is even worse in terms of economic impact for your utility. This is the one we're after. This is the one that the DMAs that I mentioned will help you with. You find this leak when it's small before it finds you and blows up the street. And there are many good techniques to in tandem with DMAs to find these leaks. There's lots of good acoustic and digital correlators that we can use to help us find this leakage. And I'll show you some of that technique later on in the presentation. So with that understanding, now hopefully I can talk about leak runtime. And really what we want to really focus on here is the awareness piece of leak runtime. So you look at leak runtime, it really, how long has the leak been running? There's really three categories. First of all, you need to know you actually have a leak. That's the awareness time. So when do you actually know that you have an unreported leak that's, basically wasting water below ground that you cannot see? So we want to try to really minimize that time. That is key for leakage control. But then once you do, know you have a leak, then you must go dispatch a crew to actually locate it in the street before you dig it up. So that's the crew you'll often see with the geophone and the nice headphones on their head, and they'll go out and they'll actually pinpoint, put X on the pavement, and hopefully the next day or two a crew will show up and actually repair that leak. But each one of those takes a certain amount of time. Sometimes, awareness could take weeks, could take months. Location could take even a week sometimes, and sometimes it might even take you a week to get a crew out to repair it once you know where the leak is. But in best practice, certainly, you want to minimize all of those three blocks of time because money is being wasted during that time frame. So to further emphasize that, I want to show you two real leaks that were experienced by Halifax Water. And this is quite some time ago. I think these slides will look at my own presentation back in 2006, so quite some time ago. But here's what happened in two actual leakage incidents. So you look on the bottom left here, this happened on August the 16th, And this one was reported. This leak only ran for 1 hour. And that was quick for us to get out and shut down right away because it was a massive leak. We lost 200 cubic meters. So that's a lot of water. And basically, yes, it kind of blew up the street. So easy to find, it finds us. The other one is a more difficult one to find. This is the unreported leak here to your top right. And this basically shows you leakage occurring. And I want to pinpoint out some things here because we had to recognize that this is what we'd call normal day. You can see the diurnal curve, which keeps repeating itself, each day, how use is actually happening within your system. But here's your night flows, and this is what you had to pay attention to. So unfortunately, this leak ran for 9 days. And I say unfortunately, some people might think that's pretty good, but believe it or not, we should have stopped that leak after no more than 2 days. Once we see this increase in night flow, we should have been on that to fix it. So I'm actually, I'll say, airing some of my dirty laundry to show you that this really should have been dealt with earlier. Now, what happened? And we kind of joke about it a little bit, perhaps, but it was serious at the time because we're wasting money. The superintendent went on vacation right here, and he left somebody else in charge. And they didn't necessarily look at the screens, the SCADA screens, on a regular basis like they should have while he was away. He came back to work after being off for a week, took a quick look, and he gave his staff hell. He gave them a hard time, to say the least. There was a few, I'd even say, curse words used to describe his feelings. And he immediately sent the crew out to find the leak. They did, and brought it back down to normal. Now, why is this important? This leak was running for 9 days, and our calculation showed we lost basically a little over 1,000 cubic meters. In other words, we lost 5 times as much as that reported leak. 5 times as much. Now, if you don't have a modern system to monitor, many of these leaks could go on for weeks or even years. So picture how much money and how much resources are wasted by unreported leaks. So that is why the methodologies that have been promoted by IWA are so important to adopt, because in the end, they save you time, money, and resources. So there's the difference between reported and unreported leaks to really drive home the point. So what is all that about, managing your leakage runtime? Because, if you don't have your systems in place, those leaks could go for a very, very long time. So, of course, the key to managing these leaks is for the overall reduction of real losses is to be aware of them, know that they're out there, but also you must have a willingness to then repair them. You can't turn a blind eye to leakage that you discover. And of course, the key to finding the leak is to find it early and find it small, because then you've got less economic losses and you'll have less disruption, because then you can actually plan this repair. You don't have to be reactive to rush out there, shut down your main quickly, which sometimes, by the way, causes another leak, because now you potentially can introduce, transient pressures by shutting down real fast. But if you've got this small leak, you can take your time. You can show up in a couple of days, set up your traffic control, go about it very methodically, and do a good job. So how do we become aware of these unreported leaks? As I alluded to in my opening statement, we're going to try to break up the haystacks to find the needle. And for those who've ever tried to find the needle in the haystack, it's pretty frustrating to say the least. But we've stepped back and said, with this methodologies that we see used in other areas, let's break up those haystacks and then use other technologies to find the needle. And that's really what a DMA does. So distributed areas can provide this awareness of leakage in almost, near real time. And the way we do that, of course, is we have a modern, hopefully some of you already have this in your systems, a modern SCADA system. And SCADA stands for Supervisory Control and Data Acquisition. And that, of course, is the software, hardware platform that operators use to monitor and control equipment and instruments within their systems. Key for, of course, to look at what happens at the nighttime. I already showed you some of that night flow that we pay attention to. What happens between 3 and 4 in the morning is critical for understanding water losses, because that's when people should not be using the water. And of course, we try to break up our area of our distribution system into zones where we can use traditional acoustic leak detection actually to go out and find the leak once we know which zone has the leak. And in the end, if we can measure it, we know we can manage it. And that's really what the methodology is all about as well. There's several metrics you can use beside even the infrastructure leakage index. There's also liters per service per connection. And and yes, you know, if you're going to use a percentage, you could say, what is your percentage of non-revenue water? And that's a very, you know, general metric that often people look at first. At least it gives you a sense of what the size of a problem you're dealing with. So here's a typical DMA that Halifax Water has in their system. And I like to highlight this one because this one is the most expensive water that Halifax Water produces. The water that comes to the customer here is boosted 3 times. So there's 3 pumps involved, from the lake to the treatment plant to the hill, and then from the hill, another booster to the customer. So very expensive water to produce. So I like to showcase it as for its importance. So I want to draw your attention to what we're seeing by the SCADA system in this zone here. And this was just a typical, you know, snapshot in time. If you look at the top right corner here, this is a SCADA graph that we can actually see in, you know, continuously. We actually get a reading every minute. There's readings on flow and pressure coming from this zone. Okay, so this shows you the diurnal curve. I mentioned the repetitiveness. There's your night flows. There's 3 nights that you can see where water losses are down around 20 cubic meters per hour. Okay. We also do what we call a bottoms-up calculation to indicate, well, what really should be being used. You know, a combination of yes, some background leakage, and, you know, the odd person that gets up in the middle of the night and uses the washroom. Certainly for a fellow of my age, that would be a normal thing for me to do. But nonetheless, this is our minimum calculation, and we think that should be being used at nighttime. And I tease our engineers, they've got it to 2 decimal points here. You don't have to get that carried away. But let's say it's 19 cubic meters per hour. Comparing that to the graph, it looks around, you know, 20. We've got ourselves a pretty tight system. So here's a case where I don't need to worry. I can sleep at night looking at this graph. I know that it's in good shape. Okay, so there's how we make good use of our SCADA system in combination with our calculations to determine what our night flow should be. And this just shows down below here the attributes for this DMA. It's got about 27 kilometers of pipe, about 155 hydrants, and around, you know, almost 3,000 service connections, and so on. So we have this for every DMA, of course, in our system in Halifax. So we have a good sense of the range and size and complexities of our DMAs. So this is a nice blow up of what we see actually at Mount Edward. This is the DMA I just showed you, but easier to see on the eyes here now what we're seeing from a screenshot from our SCADA system. And you can see this nice diurnal curve, and you can see that nice night flow, you know, around 20 cubic meters per hour there, just under that probably at night flow. So we know, like I say, we've got a tight system. But you can really tell a lot by looking at this curve, what's actually happening in this area of the distribution system. This is a residential neighborhood. So you can clearly see that there's 2 days here that are absolutely identical, and 1 day that's not quite the same. And there's some smart people, I'm sure, watching this here now that can tell me the 3 days I'm talking about. 2 are absolutely identical, and 1 is definitely different. You can see some lag in the morning in particular around water usage, and kind of more usage during the day. So the obvious answer is this is a Sunday, this is Monday, and this is Tuesday. And this is the behavior you would expect to see. So if you see that, you know, in your residential neighborhood, you're probably thinking things are normal, and they are indeed with a graph like this. I'm not showing this for you to try to pin down and read anything on this, but I want to show this because this is the entire distribution system for Halifax Water, showing all the different DMAs. And as you can see, they come in different shapes and different sizes, and they're all around the entire network of Halifax Water. It is fully sectorized. So all of this system is broken up into DMAs within the Halifax distribution system. And what you're looking at is approximately 75 DMAs here. And again, they all come in different shapes and sizes, and that's okay. There is no perfect size for a DMA. And I'll try to explain that in the next slide. Basically, in many cases, and this happened with Halifax Water, many of our DMAs were predetermined because we had to control pressure. We had pressure zones where we had to pressure reduce in particular. And there's a lot of, hilly topography in Halifax area. So we had to be careful that we pressure reduce from our treatment plant, which is way back in the woods, about 30 kilometers away. And water flows by gravity. And as it comes to town, it of course increases in pressure, and we have to intentionally reduce pressure before it reaches the customer. But in some cases, of course, because it's hilly, we may pressure reduce in some areas, but there's other areas, just like I showed you, where we had to boost as well. So these are automatically a great candidate for DMA, okay? Because they're already set up with isolation valves, that they've been isolated from other parts of the system. And that's key to DMAs. You must isolate so it truly is standing on its own in terms of water flowing in and water flowing out. The question always gets asked about DMA, is a smaller DMA better? I say, sure, if the opportunity exists, there's no question you'll do better, but don't get carried away trying to make them all small, because you may not find that it's necessary. It will, of course, improve your resolution and obviously reduce your leakage runtime where you need to go smaller. And this DMA size really is based on many factors, including your acceptable leakage runtime and your night flow analysis. If you've got a big DMA and you look at your night flow and say, wow, it looks like there's not much going on here, then fine, you don't have to break up the DMA into smaller sectors. So it really depends on what you see in a local context. So here's an example where Halifax Water discovered that their DMA was too big and they were not able to figure out what was going on. And this is an area right on what we call the Halifax Peninsula. So it's very close to the downtown area of Halifax. There's lots of activities in the nighttime. There's hospitals, lots of water use in the nighttime. So it makes it a little more difficult to try to figure out what's going on. So we started with this DMA when we first got going in the turn of the century. We had a 114 kilometer DMA, which yeah, that is pretty big. So we said, okay, well, let's do something about it. Let's break up the haystacks right now. We felt that this was too big for us to find the needle. So here we go. What we do, we basically isolated a section and we closed a lot of valves that were already, open and flowing freely. And we installed 3 meters across that boundary because we wanted to make sure we're measuring flow going into this sector and flow going out. Okay, so we always know what's happening within the zone. Likewise, in the northern part of the peninsula, we've dropped in 2 meters and again, closed a bunch of valves, did some checks to make sure, water quality wasn't impacted, and fire flows. We did some testing to make sure fire flow wasn't impacted. And now we've got ourselves 3 DMAs automatically. So by doing the work to get 2 in place, by default, the third one comes to bear. So you can see now we've got a 46, a 36, and a 32 kilometer DMA. So basically by installing 5 meters, we were able to do that. That costs money, but it's money well spent. So here's what it cost us to put in a typical meter at the time. These are costs back then. We're talking approximately $25,000. It's basically a precast manhole with a mag meter installed. And these are mag meters, of course, that are meant to be immersed in water. So if there's any high groundwater table, they're not impacted. We also show there's a tap there for a pressure transmitter, and you can see that clearly on the pipe. So we also get pressure measurement at the same location. What a novel idea. It's great. It gives us more information and helps us manage our system. And here's the pole mount remote terminal unit. This is basically the device, the logic controller that sends back the information by the antenna you see there on the telephone pole back to our head office. So in this case, we use broad spectrum radio waves to send that information to our headquarters, which of course in our case is very cost effective because basically it's free. So we're able to capture that through broad spectrum radio. So you can see from that investment, we put 5 meters, that's $125,000. The payback for that would probably be about 3 years. And after that, it's gravy. Then you're just making money hand over fist. We also did some partnerships with our big customers. As you can appreciate, Halifax is a port city. The Navy sails out of Halifax, as well as there's 2 container terminals within the harbor facilities. And this is one of the areas that we provide water to the Port of Halifax at one of their piers. And we offered to do some leak detection for them many times. And we told them, look, we can give you a service. We can monitor for you using our own technologies And we can also provide a portal for you to view online if you wished. So we actually did a demonstration project with them. And this is the demonstration project where they became converts in water loss control real quick. So what you see here before you is a 24-day graph back in August of 2005. And we basically showed, ourselves, we put the RTU on their meter so we could see it in real time. Every minute we get a signal sent back with information, pressure and flow. And this is what we saw over a 24-day. So this is research to a certain extent. This is a pilot project with the Port of Halifax. So you'll notice some interesting things happening on this graph for those of you certainly with trained eyes. And sometimes I've often asked the audience when I'm delivering the presentation to tell me how many leaks they can spot on this graph. And often I get a range anywhere from 9 to 11 people that try to basically count those spikes that you see. And of course, I had to tell them all that they're all wrong. And what you see here, there's only one leak on this graph. And we're going to look at it right in the center of this graph. So here's our night flow. Everything's going along nicely. And by the way, each grid here represents 1 day. So understand that, right? This is 24 days in total. So everything's going along fairly well, decent night flow, pretty stable. And all of a sudden, the night flow kicks up. And here's something else interesting. And I'm sure you've all seen it in all of your systems. A leak does not repair itself by itself. It doesn't get better over time. It's not like a good wine that gets better with age. A leak gets always worse with age. And you can see here, it's gradually climbing and climbing and climbing. This night flow is getting out of hand to the point where we said, okay, that's enough. So we called the Port Authority, said, we've got an absolute leak in our hands. And we actually went down and we located for them. So we found it and they brought in a contractor and they fixed it. And here it is, we're back to normal. So I can assure you that's a lot of water lost there for the Port of Halifax. And as a matter of fact, we actually entered into a contract with the Port of Halifax after that to provide this service on a fee for service basis. And our annual fee to monitor all their locations basically is paid for if they'd fix this one leak in 2 days. Okay, so that's how economical it is, right? So picture now they've got several feeds. This is only one feed into the Port of Halifax. We've got probably 12 different feeds that we supply water through. So they signed up immediately because they saw the economic benefits to get this early detection. So if you're all wondering what these big peaks are, you can expect, of course, that we are a cruise ship call, just like the Caribbean, believe it or not. Although I think I'd rather go see your ports if I was allowed to these days. But nonetheless, many of these are cruise ships that take on water. And they take on water in Halifax because we've got one of the best water qualities at the lowest price, and which is obviously quite nice for these cruise ships. So that's what this is. These are cruise ships taking on water. So I mentioned some of the gear that we use to find the leaks. So once we know or aware we have a leak, we send a crew out to pinpoint it. And some of the basic techniques being used, this guy here is using a ground microphone. So this is what I'd call the traditional method. It basically relies on the person's own hearing. Obviously, you need to have good hearing to do these things. But over time, you get used to hearing different sounds from different types of pipes, everything from ductile to cast iron to asbestos cement to pre-stressed concrete cylinder pipe, and even, yes, PVC. But PVC is very difficult for leak detection because you do not get much sound attenuation. But ductile and cast iron, you'll absolutely find leaks pretty easy with this technique. So we can listen on hydrants. Sometimes the hydrant branch itself might be leaking, but we can listen, and we'll listen on all our hydrants, and we can zero in on an area where we know we've got leakage. We can also tag, that's a valve that this person is tagging here. So you can see the operating mechanism. This is the T bar that we can drop down to operate the nut. So it gives us a physical contact with that valve, and we can listen on it and we can hear and know we've got a leak. The gear down here is a little more sophisticated. This is a digital correlator. And this one, basically you hook up between 2 points where you have a physical contact with your system. And often hydrants are absolutely the best way to hook up. It's a lot safer for starters. You're not out in the middle of the street. And you basically hook up the 2 hydrants and you use filters and technology to listen for the sound. So now you're not relying on the human ear. You're now letting the digital ears pinpoint your leak. Okay, and sometimes this is used to find the real small leaks or the difficult leaks where there's a lot of background noise and you're competing with other noises in the neighborhood, things like pumps, transformers, those types of things. These come with filters, you know, basically artificial intelligence that recognizes the noise for what it is and filters it out so you can clearly see what you're looking at in terms of leakage, and then it pinpoints the leak where to dig. So these are the two most common technologies that we see right across the world. These are this is the first one we started with. These are kind of the, you know, the evolution of the so-called listening stick, and this, of course, is the new methodologies that have really come to play in the last 20 years. So I said I'd also talk a little bit about pressure management because of its importance. You can clearly see it as one of the methodologies on the strategies that OWB promotes. So there's no question, if you reduce pressure, you actually will reduce breaks. If you run your system at higher pressures, then you should expect to have more breakage. And of course, we know there's a direct relationship between pressure and the amount of leakage you can have. So if you reduce pressure, it's going to reduce your flow rates, both from active leakage, okay, the unreported leakage in particular, but also background leakage. And this is where you can save money by reducing background leakage if you employ pressure management. And I'm going to show you a nice case history of that as well. But to drive home the point, here's a water main under pressure. This is actually a leak that we did detect using traditional methods. And this leak was not surfacing. So this water was not coming up. So here's a case where we just dug the leak and we're now starting to shut down. So you can see there's a lot of water moving there. It's under quite a significant amount of pressure. As we shut down and the water column is decreasing and leaking through this location, then obviously the pressure is now less at this location and the leakage is starting to be curtailed to the point at the very end. We're almost shut down here now. The water column is not very long and we have much reduced pressure, but this sure drives home the point of the pressure leakage relationship. So there's two traditional ways to reduce pressure for the most part. Well, really, I should say there's one traditional and there's one advanced that I'm going to talk to here. One is simply to use pressure reducing valves, which have what we call a fixed outlet control. So basically it's a pilot on this valve that fixes the downstream pressure and says, this is what we'll maintain all the time. And it will basically manipulate the mechanical valve to make sure that the pressure is controlled. So it's fixed and it stays consistent throughout the day. The more advanced method is called flow modulation. And basically it allows pressure, downstream pressure to trend with the flow. So as flow is decreased, the pressure will go with it and drop as well. And when the flow increases, it allows the pressure to come up a little bit so that the service levels to the customer are not noticeable, that the customer still sees good pressure and good flow. There are, however, limits. There's a certain case where you say, nope, we're not going to let it go much further because we've reached a critical limit. It may even be based on fire flow as an important thing to watch out for. For those of you who operate firefighting systems, you know you can't let your pressure drop too low because during a fire, you could produce negative pressure in your distribution main, which will cause you a whole lot of hurt if you do that. You will have one mess on your hands. You'll be breaking mains all over the place. So here again, we show this lovely graph to get the point across that pressure can work in your favor, or it can also increase your leakage if you don't manage it. So I'm going to take you back to a research area that we tried this flow modulation to control our pressures. And this is a DMA we use called Dartmouth Central. So here it is right on the opposite side where I showed you where we broke up the haystacks in the Halifax Peninsula. Well, this is right across the harbor in the community of Dartmouth. So here's a close-in view of the DMA. And again, you can see all the attributes down here. This is roughly 60 kilometers of pipe and a little over 3,000 service connections. And right in the middle, I should explain this. You see this big kind of bare patch. That's actually a golf course. So if you're wondering why that's there, that's what that represents. So there's obviously, it's a big customer, but there's no obviously services or streets running through the golf course. So this is what we call a cascading DMA. So we have water that enters this DMA through 2 points one is called the Lehman pressure reducing valve. The other one's called the Mi'kmaq pressure reducing valve. And water also leaves the zone through 3 other PRVs, Albro, Elmwood, and Wise Road PRV. So it's a cascading. So water goes in and water goes out. And as you can appreciate, we have meters on all of these locations to make sure we know what's going in and what's going out. And of course, we have meters throughout our premises as well, so we know what the customer is using. I should point out, and shame on me that I've mentioned already, Halifax Water is a fully metered utility at all its premises, and that is pretty important when you're really trying to decide what's going on during the nighttime. And we actually have a full-fledged advanced metering infrastructure system, so we can see in real time what's happening at a premise, and so can the customer. We've actually given access to the customer, just like we did to the Port of Halifax earlier, to see what was happening in their system. A homeowner now can also see what's happening in their system. But nonetheless, here's how we tackled this in terms of pressure management. We see the lay of the land, and what we're going to try to do is use flow modulation in these 2 chambers here, Lehman and Mi'kmaq, to try to control pressure to the best of our ability. This was a project we did with the Water Research Foundation, and this is the prototype that was done back, this was done back I think in 2007 or so, quite some time ago, but nonetheless, I should point out that we've adopted and adapted since then. We've actually got different controllers now that we're using. This one initially was based on air. We used air here to control our pilot on our pressure reducing valve, when ultimately we've gone to a water system. So basically, I'll explain what you're seeing here. You see 2 pipes here. This is the one we're going to spend most of the time talking about. This is the one that we're doing our research on. This is the domestic flow. And just so you know, this is for fire flow. So if something happens, there's a huge fire and it calls for more water, this detector check valve will open up and all kinds of water will flow, and that's all good. And the fire will be hopefully controlled by that huge amount of water. But during most of the time, we have domestic water flowing through here. We do pressure reduce, and here's the PRV you see there in the foreground. Okay, I can even read the tag. It's a Singer pressure reducing valve, so it uses a diaphragm to control pressure versus a piston type that some of the other manufacturers use. And over here to the right is basically our pilot, okay, that controls how the valve opens and closing. And you see on top of here, this is called a bias plate. And this is here where we manipulate the pilot so we can control the pressure downstream based on flow. And of course, in the middle, here's our flow meter. So we know exactly what water's coming through the system. And of course, here's all the brains of our system here, where we use artificial intelligence and programmable logic controllers to make sure that the system is watching all the different data points and knows to increase gradually and slowly whenever there's any change in what's happening downstream. Okay, so obviously it's set up like this because in the end, we end up mounting this one inside a remote terminal unit, but this is the prototype, so you can see it's mounted there on plywood, just for the purpose of research. All right, so here's what we did with that lovely research project, and this will take some time for your eyes to adjust, and all the engineers watching this are going to have a great time, because this is a graph after all, and engineers live for graphs. So this is your time to pay attention, engineers, if you're watching. But basically what we have here is a combination of pressure and flow over roughly a 4-day period. Okay, we have our pressure here. You can see on the side a scale from 0 to 600 kilopascals. Okay, so the blue is the pressure. What you see in kind of the reddish color is the flow in cubic meters per hour. And again, just like I showed you in other graphs, we've got this diurnal curve happening, you know, that we're seeing across the 4 days. We're seeing some variation here, obviously, in the night flows, and we're doing that intentionally as part of the research. And I always joke with the audience, I always tell people, do not try this at home. We did this in the name of science. So we took some risks to show people the different ways you can or cannot manage pressure within your system. So we started actually with our true flow modulation, where we have a very nice control of our downstream pressure. It does move with our flows. Here's our night flow. So we bottomed out here at roughly 100 cubic meters per hour. And yes, folks, there is some active leakage there, and we actually did find some leakage in this system afterwards. But nonetheless, there's your night flow, and there's your morning peak. People go to work, and then they come home, and then they take another peak again around supper time. So this one clearly shows a nice pattern that you'd expect in this DMA. It's a combination of residential and commercial. So this one behaves a little different than the one that I showed you earlier. So here's, we're starting off with advanced flow modulated control, but then we decide, okay, just for the sake of science, let's have no control. So let's open up the valves at Lehman and Micmac and just let water flow freely into the system from the adjacent zone. So we've totally changed the hydraulic grade line feeding this zone. And you can see how much by ultimately, and you'll see what happens when you do that. It's actually dangerous to do that, because you can see now in the nighttime when there's low demand in the system, you'd expect here the pressure to go to highest with no control. There's no control. It's just coming strictly from the reservoir up the street. It's coming from the reservoir I showed you earlier at Mount Edward. So open to the reservoir, floating on the reservoir, huge issue there with pressure. So we saw a difference here of roughly 200 kilopascals, which is roughly 30 psi. So we've introduced an additional 30 psi, which is quite dangerous. But you can see how the system reacts. Okay, with high demand, the pressure will drop. With low demand, like here, the pressure will be at its highest. So you can see the difference. Now we have 103 cubic meters per hour of background and active leakage at this position. So then we went to the traditional fixed outlet. This is where I tell you, you put your pilot to work to say, are going to set it at a specific downstream pressure all day long. And I can tell you, the valve is doing its job. Look at this pressure. Very consistent all day long. Okay. Now, what happens? You do a little bit better than what you did before. You went from 103 cubic meters per hour down to 79 cubic meters per hour. So this is a good way to control pressure. Make no mistake. This is the traditional method. The flow modulated method, which is the advanced method, shows you where you can actually save leakage all day long. Because not only will you find it at nighttime, and you can see here that the flow now goes down to 70 cubic meters per hour. And look what happens to pressure. You intentionally drop the pressure. And that's why if you drop the pressure, you have that corresponding drop in flow. The pressure flow relationship. Here it is again in real time. So you can also see some nice little things happening during the daytime. So you can see, again, some drops in pressure here intentionally as flow goes down. So you're actually saving a little bit of water during the day as well. Same thing over here. Okay, you're letting that pressure, see that pressure drop a little bit more than what it was the day before. So you're actually getting savings all day long, but in particular, you're getting savings at nighttime. So that now is the tradition. This is now a method that's being used now in different zones of Halifax Water, and other utilities have caught on to this advanced method. So I'm getting to, I appreciate your patience so far. I'm getting close to the end, and one has to ask, well, why the heck do we even bother to do this? Well, I like to say it's because we have triple bottom line results. In other words, we get economic benefits, we get social benefits, and we get environmental benefits. So right off the bat, I can tell you it's very highly cost effective. Right now, Halifax Water is saving $650,000 a year by having this modern leakage control program. And when they started, they were inputting around 170 million liters per day, and now they're down to 130. So they've captured 40 million liters per day in leakage. So that represents a lot in terms of environmental stewardship. The other thing to recognize is that water loss control improves public health protection, because a leaky system is prone to contamination. Every time you have leaks, you have the potential for negative pressure, you have potential for contaminants to get into your system. So if you control your leakage, you will do better in terms of providing safe drinking water. It does improve the level of service to your customers, because you find these leaks now in a proactive manner. I mentioned, of course, a lot of times you don't have to go out in a panic to go out and shut down the leak in a hurry. What we often do, we'll find the leak one day, and then once we've found it and pinpoint the leak, our crews will then go around and knock on the customers' doors the day before they come to the site and say, we're coming tomorrow to fix the leak. If you need to take off some water, we advise you to draw it off in the morning before we show up. You know, so at least you can have your breakfast and good shape, have a shower, go to work. And by the time you get home for supper, which is, of course, now it's your time right now, the leak is fixed. And they come home, have their supper, and the water's restored. So the service restored. Customers thank us immensely for that, and they're very kind of amazed that we can provide that level of service. The other thing to recognize is in many cases we've seen utilities, instead of going after the leakage when they have supply capacity issues, they try to find additional supply or increase their treatment plant size. And that is wrong. That is a very expensive way to try to get more capacity into your system. I haven't seen a case yet where it's cheaper to build a new treatment plant or find a new source of water than to fix the leakage downstream of the existing treatment plant. So leakage recovery is your best source for new water. So if you're having trouble, you know, trying to serve new areas of your municipalities, if you control your leakage, you will have available capacity that you now can extend that service to other areas of your municipality. And last but not least, this reduces the liability to water suppliers. You sometimes will be taking a course, and it'll happen to you if it happened already. Sometimes you might end up in a court of law because of the damage caused by one of those big water main leaks that blow up the street. And it's sure great that you can point to a best practice that your utility uses when the judge and the other lawyers quiz you about your approach to water loss control. And I have had that experience myself. And I have actually had in a court of law, a judge call me a reasonable man. So I always use that phrase because we know that when you're in a court of law and somebody calls you a reasonable man, you're having a really good day. That is as good as it gets in a court of law. So in terms of lessons learned, I think this is important for anybody who's going to embark on this. This is not for the faint of heart to just, you know, jump in. You had to recognize that this is as much to do with change management as it has to do with technology. I showed you a lot of wonderful technology, and yes, you can put it to good use, but you better bring your people and your processes along with it. You need to train your people. You need to have committed people. You need to reward your people for doing the good work that they need to do. And also, of course, lay down those clear processes by following a strict methodology. Very important to have project champions. And I think you all know that when you ever want to try to get something done, if nobody's going to stand up and say, I'm going to lead this initiative, you're going to have a hard time getting it done. So try to identify that champion within your ranks, educate them, make sure they're formally trained in the processes, and get them to basically be the, train the trainer. That person then can take the message to others and make sure everybody's doing a consistent approach. Always involve as many people as possible. I know that's challenging sometimes. It's both the blessing and the curse of water loss control. Believe it or not, it's important to get cross-departmental teams involved. Get your meter department, get your treatment plant people involved, get your finance people, your distribution system. Everybody needs to be involved, which also makes it challenging because there's a lot of coordination to do. But you can do it. And start, yes, with a committee. Yes, you'll hear it first from me. Yes, it's okay to form a committee to chase this down. But I can tell you now, Halifax Water today does not have a committee for water loss control. You may say, oh, darn, how disappointing. They don't need it anymore because the culture of water loss control now is so embedded. It's just part of their daily life. They do not need anybody to ask them how they're doing with water loss control. They just are now doing it through osmosis. It is part of their very DNA to find leakage and to control leakage. Okay. And I always tell people, don't be afraid to try something different. If you think you're going to keep doing the same thing over and over again and get different results, I'll suggest politely you need to go get help somewhere else. That is what we call the definition of insanity. You're not going to get a different result by doing the same thing over and over again. So try something different. Take some risk. Take managed risk and try to adopt a new way. Other unexpected benefits that we realized is all of a sudden we had these partnerships with our customers. Our customers, actually, we have a higher level of satisfaction from our customers because of this methodology. And as I said earlier, we have intimate knowledge of our system. We understand our system better than we ever did by becoming experts in water loss control. And because we're a regulated utility, we often use a lot of the data from our program to support our cost of service for our rate structure with our regulator. And I can tell you that my friend Valerie can give you a whole presentation on that some other time, or even myself. Maybe that's something we'll do someday. Valerie, is do another cost of service rate structure presentation as well, because that is a lovely topic. And this benefits from this intimate data that you collect as part of this program. Last but not least, and this is something we often forget to do. Yes, we obviously should measure performance. You need those metrics to say how you're doing, set your goals based on those metrics. But when you reach those goals, absolutely you should celebrate and reward that success. And sometimes we don't do that enough, especially in the public sector. Sometimes it's even frowned upon. But ironically, the private sector does this all the time. Here's where we can take a lesson from the private sector and apply it in the public sector, and it works very well. So to get my point across, we do use the infrastructure leakage index at Halifax Water to measure performance. When we started back in 1998, 99, we had an infrastructure leakage index of 9. And by 2007, 2008, we had it down to 2.5, which represents that recovery of 40 million liters per day in leakage. So we had some fun along the way. You can see there's a lovely little hamburger there showed below the graph point of 4. Basically, I said that we'll certainly look to celebrate our success. So when we hit that 4, that was a pretty significant milestone for us. Took some time to get there. Basically, that was, as you can see, 5 years to get there. And I threw a barbecue, and I got out and put it on and barbecued some burgers and some steaks and got some salads, and there was quite a mood of like a joy amongst the crew. And then, of course, as general managers do, stand up and you make a little speech about how they did it and where we're going to continue to chase our leakage. So I made it a point to say that we're not done yet, that our goal actually was to get at least to 3. We wanted to at least get to an infrastructure leakage index of 3, because we thought that would put us in what we'd call a position of world-class performance. And there was a person at the back of the room that yelled out to me that said, "That's great, Carl, but what will you do for us if we get an infrastructure leakage index of 3? So I answered back and asked the question back to him and said, "Well, what would you like if we reach an infrastructure leakage index of 3? And he came back right away and said, "I would like you to buy lobsters and have another feast where we'll have a big feast of lobsters." And I said, "Okay, make it so." So they went hard for the next couple of years, and by 2 years later, we were down to a 3. And I went out at $1,000 of lobsters, and we boiled them up and had a great time celebrating our success. And you can see we didn't stop there, we kept going. And I can say we're probably not going to go too much further. We may be able to get down to 2, because I mentioned something very important. We want to be at our economic level of leakage. And of course, we have a regulator that allows us to spend money on these things, but they're interested in making sure that we're getting return on our investment. So I'd suggest politely for Halifax Water, 2 is within reach, but after that, it'd be hard for us to make the economic arguments. So with that, that is my presentation, and I would be very pleased to take any questions from anybody that has something to ask. I see some questions in the chat box, so perhaps I'll start there first. I see here there's a question there: water audits and DMAs. Does this involve audits of customers, including households, businesses, etc., within DMA? If so, is it by random or targeted? Basically, we do the audits of our different DMAs. We actually can do an individual audit for each DMA if we wish. And just for a bit of fun, even at Halifax Water, we broke up our regions into 3 geographic areas: east, west, and central. So the crews would actually have a bit of competition to see how much leakage they could find. So you can go smaller if you wish. You can report it as a utility, you can report it as a geographic area, or you can report it as a DMA. And of course, with some of our larger customers, they also could do that. So I mentioned the Port of Halifax. They absolutely could set up their situation to report metrics within their own private distribution system. You appreciate that they have a big internal distribution system throughout the pier, and we meter them at the gate, so to speak, and they're in charge, of course, of their own distribution system. So they as well could do their own audit if you're a large customer. So that is absolutely part of the approach. Are there incentives for water conservation? Certainly for us, conserving this water, there's definitely incentives for the utility. And by the way, we actually do give some incentives for individual staff that actually work on these programs. As part of their goals and objectives, they actually do have cash on at risk to reach their goals and objectives. So we do actually have some incentives for our staff, for our managers in particular. But in terms of traditional water conservation, like low flow toilets and water dams and faucets, we promote that, but they're available everywhere. They're very easy to get. We do have some programs we've worked with other NGOs to promote, and we've made some contributions to those programs. So we have actually provided, of course, a lot of these devices at less than cost to our customer. So there's a comment here. What are some good tools or valves for electronic monitoring of water in your system? What's a good resource to learn how you set up a good monitoring system like this? So that's a great point, certainly, and I'm sure some of you are at different stages in your journey, but the more that you basically engage your technology there with your staff, the better. So at some stage, hopefully you'll have a very modern SCADA system and good instrumentation that measures, pressure and flow, possibly even pH. If you're looking at monitoring, water quality, there's lots of amazing devices that are coming to bear now through the market. Obviously, the smart devices are coming fast and furious in the utility business. You'll see them extensively in the electricity business, in the gas business, and yes, they're coming out to the water and waste business. So there are lots of really good instruments. There's data loggers as well. I don't know if any of you on this call have ever used data loggers. Sometimes they're very useful to put down valve boxes and listen to noises. And this is, of course, artificial intelligence listening for noises. And sometimes we use those in places where there's a lot of background noise, especially like, very congested areas where there's a lot of traffic at night, a lot of noise coming from pumps, transformers, cooling systems, and data loggers can absolutely be used. They're great electronics in those cases. So lots of tools out there. Again, I'll ask if you can get your hand on that M36 manual. It will be one of the best purchases you ever make. And they talk about all of those different tools. They talk about the SCADA system and how, of course, you can incorporate these to make yourself a better utility. So if there's any other questions, though, directly from anyone, I would be pleased to take them. Any other questions?
I don't see any other questions, Carl.
Now, it's always tricky when you do a presentation before supper time. They're probably getting hungry now. So
no, I think that was a very fabulous and very comprehensive presentation, and I think that it was well received in my mind. I think of course we have the recording, so those who missed it we can share. But there's some very valuable information, and of course, water audits and non-revenue water, managing leakages is becoming a very core area in the operations of most utilities within the Caribbean region. And so I think it is a very good presentation that is quite relevant and useful for all of us. So
I think, Ignatius, very often when we talk about water leakage and non-revenue water, we're always talking about leaking pipes. And of course, that's part of it, but I don't hear so much about the district metered areas. So that's why I was really keen for Carl to share his knowledge and experience about the district metered areas, because it's so much a part of it and so critical to good water leakage control. I was on when we were talking with Mark Barnett the other day from Jamaica, and I asked him, do you have water metered areas? And he said, yes, we do. And I think they have about 190 areas that he talked about throughout Jamaica. So they're on board with this, but I know that this is something a bit new to a lot of utilities in the Caribbean. So it's something that I think we really need to focus on if we're going to do water leakage well and reduce our non-revenue water in an easier way than we're doing now.
Yeah, what this does, it allows you to reach that sustainable level and keep it there. That's the nice thing about the DMA, right? It's it does make it easier once you get to that economic level of leakage. You can maintain it without much extra effort once your system is in place.
Yeah, as it stands, as I said, quite a number of utilities are getting into doing putting the non-revenue water high on the agenda, and in many of their strategic plans, that is included. And so I think once one utility is going to undertake a non-revenue water project, the district metering is going to be key, a key factor in all of that. And I think they have been trying to, I think some utilities who have started in fact with their metering systems, as well as trying to have the mapping of their systems, which is, as you mentioned, the SCADA systems. A number of utilities are trying to get in there. But it requires, as you indicated in your final slide, the need for bringing as many people on board as possible, because it is a holistic approach. It cannot be just one unit. It has to involve everyone in the utility across the various units, as well as having the customers on board to understand. So it involves the education and communications with everyone.
Absolutely. It's really a corporate initiative, right? You have to kind of look at it in that way, right? It's not just one department doing it. Everybody's got to be aware and buy in. Yeah, so it's a great point, Ignatius.
Yeah, so if any of the utilities that are listening today want some help in, what do you do to get this started, or we've got it started, how do we do this? Operators Without Borders is there to help you. We can work remotely right now, but later on perhaps in person, and come and help you, look at your systems and what you're doing. So any help we can give you, we're very happy to do so.
And anybody else has a question that they're too shy to ask today, by all means, you can drop me a line by email. So you can certainly share my email address, Ignatius.
Yeah, we'll do.
With the participants, and if they got some questions, then I would be pleased to entertain them.
Thank you very much. So, well, this brings us to the end of today's session. And as we were trying to find this needle in the haystack, and I think, Carl, you certainly helped us to dig deep into the haystack and get close to finding that needle, which is non-revenue water. And we'd like to thank those participants who stuck with us. And thank you, Valerie. And thank you, Carl.
Thank you, Connie. And you hope you have a good supper and a good evening, and stay safe and be calm and be kind to whoever you meet. So we'll talk to you again soon.
Thank you. Ignatius Jean, the Executive Director at CAWASA. And this is the end of our Wednesday webinar. Thank you very much. Over and out. Bye.
Cheers.
Bye-bye.